Now, let us consider the situation where my random vector is absolutely continuous. So, let x is x1, x2, xp, which is absolutely continuous random vector. Its joint PDF is fx and support is sx. Let s1, s2, sk be open subsets of Rp such that Si intersection Sj is phi, and union of Si is nothing but Sx naught, where Sx naught is the interior of support of x. So, what we are doing over here is we are assuming that support of random vector x is a union of disjoint open sets in Rp. If that is the case, suppose I consider p functions Hj from Rp to R are p functions such that on each Si H is 1 to 1, and suppose its inverse transformation on Si is Hi inverse t, H1 I inverse t, Hp I inverse t. So, what we have done is support of the interior of support of S suppose is a union of k disjoint open sets, and in each of these open sets, suppose my transformation H is equal to H1 H2 Hp is 1 to 1 with inverse transformation given by Hi inverse t, which is H1 inverse t, Hp I inverse t. Further, suppose that Hj I inverse t have continuous partial derivatives, and suppose their Jacobian determinant is given by this. So, suppose their Jacobian is basically look at the Jacobian of these quantities with respect to T1, T2, Tp. So, that is partial derivative of H1 inverse t with respect to T1, partial derivative of H1 inverse t with respect to Tp. So, first row consider all first order partial derivatives of H1 inverse t. Second contains all partial derivatives of H2 inverse t. The pth row contains all partial derivatives of Hp I inverse t, which is the pth coordinate of the inverse transformation. Now, define H of Sj as Hx, which is H1x, H2x, Hpx for x belonging to Rp, such that x is in Sj. And let us say Tj is Hj of x1, x2, xp. So, what we have done is we had a random vector x, which is x1, x2, xp. Using this, we have considered k function T1, which is H1 of x, which is T2 is H2 of x, and Tp is Hp of x. What we have assumed that this whole transformation H, H1, H2, Hp is 1 to 1 in each of the sets Si, and Jacobian is given by this. Then T is absolutely continuous, and its joint PDF is given by this summation j is equal to 1 to k, and this is the term corresponding to Si. What is happening in Si? Inverse transformation is, this is the term corresponding to Sj, because j is equal to 1 to k. What is happening in Sj? Your inverse transformation is H1 j inverse t, Hp j inverse t. So, Fx at the point of inverse transformation. Then whatever is the Jacobian, so that means you look at Hj inverse t's and consider their Jacobian, and then indicator H of Sj. So, that is what we did. Similar result in the case of one dimension. In that case, there was no Jacobian, there was only del by del t of Hi inverse t. So, this is given by this. Now, in the case where my transformation H is equal to H1, H2, Hp is 1 to 1 in whole of Sx, there will be only one term over here, and in that case, this result simplifies to the following result. So, let x is equal to x1, x2, xp be an absolutely continuous random vector with joint PDF fx and support Sx. Suppose that Hj from Rp to R are p functions such that H is equal to H1, H2, Hp from interior of support to Rp is 1 to 1. So, it is 1 1 in whole of the interior of the support with inverse transformation H inverse t, which is H1 inverse t, Hp inverse t. Further, suppose that Hi inverse t have continuous partial derivatives and the Jacobian determinant, which is del H1 inverse t, del H1 inverse Tp, del H2 inverse t del T1, del H2 inverse t del Tp, del Hp inverse t del T1, del Hp inverse t del Tp is not 0. Then T is equal to T1, T2, P, Tp, and I also define H of Sx naught as collection of all those Hx such that x is in Sx naught, and Tj suppose is Hj x1, x2, xp. So, I have T I have p random variables t1, t2, tp, which are defined in terms of these p functions h1, h2, hp. Then the random variable t is absolutely continuous with joint PMF given by this. So, here only we have one term fx h1 inverse t, hp inverse t, determinant of Jacobian, indicator h s x naught t. So, to see an application of this result, let x1 and x2 be ID random variables having common PDF, which is 2x if 0 less than x less than 1 and 0 otherwise. Find the distribution function of x1 plus x2 and hence find the PDF of y. Find the PDF of y directly using the Jacobian method. So, y is x1 plus x2. So, let us first try to find out the distribution function of x1, x2. For that, first let us see what is a joint PMF of x1, x2. fx1, x1, x2 would be same as, because of independence, fx1, x1 into fx2, x2. But fxx is 2x if x is between 0 to 1. So, fx1, x1 multiplied by fx2, x2 would be 4 times x1, x2 if x1 is between 0 to 1, x2 is between 0 to 1 and this is 0 to otherwise. My y is x1 plus x2. So, clearly support of x is 0 1 cross 0 1. Since y is x1 plus x2, support of y would be 0 comma 2. Now, for y belonging to R, I look at what is f y y, probability y less than or equal to y, which is same as probability x1 plus x2 less than or equal to y. So, that means I have to integrate the PDF over this range. My PDF is non-negative only in the range x1 between 0 to 1, x2 between 0 to 1. I have to integrate this PDF in this range, which is 4x1, x2, and the range of interest is x1 plus x2 less than or equal to y. Now, here if I fixed x1 as a free variable, x1 as a free variable first goes from 0 to 1. For fixed x1, if I see x2, x2 is between 0 to 1 and also x2 is less than or equal to y minus x1. So, this is what the desired range is. So, that means this gives me 0 less than or equal to x1 less than or equal to 1, x2 is greater than or equal to 0 and x2 is less than or equal to 1 as well as y minus x1. So, this is less than or equal to minimum of y minus x1 and 1. But for this range to be non-empty, each of these terms should be greater than or equal to 0. So, that means y minus x1 should be greater than or equal to 0. So, that means x1 should be less than or equal to y. So, that means this gives me x1 greater than or equal to 0, less than or equal to minimum of 1 and 1. And in that x2 would be greater than or equal to 0, less than or equal to minimum of y minus x1 and 1. So, that is what I do. So, I fix x1 as a free variable, x1 as a fixed variable can go from 0 to minimum of 1 and y1. So, this is what you get. Now, note that my support of y was 0 to 2. So, clearly for y less than 0, f y y is 0 and for y greater than or equal to 2, f y y is 1. For y between 0 to 2, we have seen that f y y turns out to be this. So, now I have to break various cases depending on whether my fixed y is less than 1 or bigger than 1. So, for y between 0 to 1, my range would be 0 to f y y would be 0 to, in this case it would be not x1, this would be because y is smaller than 1. So, this will be 0 to y, 0 to, now if x1 is less than y and y is less than 1. So, y minus x1 would be smaller than 1. So, y minus x1 would be smaller than 1 because y itself is smaller than 1. So, y minus x1 would be smaller than 1. So, it will be range and you get y to power 4 by 6. For y between 1 to 2, it would be 4 times 0 to y minus 1, and in this case you can easily see that minimum of 1 and y minus x1 would be nothing but 1. So, you get as, so for y between, let me repeat it once again over here, if y is between 1 to 2, so that means y minus 1 is greater than or equal to 0, less than 1. So, in this case, since y is bigger than 1, this range would be from 0 to y. So, x1 is 0 to y. So, that means y minus x1 would be greater than or equal to 0 and less than or equal to y. So, if you break this range, it becomes 0 to y minus 1, 0 to 1 plus 4 times 0 to y minus x1, x1, x2, x2, x1. This becomes x minus 1 whole square. So, here what would happen is depends what your x1 is. So, x1 was going from 0 to 1. Now, 0 to 1 further range can be broken into 0 to y minus 1 and y minus 1 to 1. When x1 is 0 to x1 is less than y minus 1, minimum of 1 and y minus x1 turns out to be 1, and you can easily check that this quantity will be this. Through simple calculations, this turns out to be this. So, I have got my f5y, which is this quantity. Now, clearly this is differentiable everywhere except at the point 0, 1, 2. So, I look at their derivative and I put that as f5y, which turns out to be this, and one can easily check that minus infinity to infinity f5y dy turns out to be 1. So, this is absolutely y is absolutely continuous and its PDF is given by this. Now, suppose I have to find the PDF of y is equal to x1 plus x2 directly. For that, what I do is I define another variable z, which is x2, so that the transformation y x1 x2 to yz is 1 1. That is what we are doing, because to make this transformation 1, I will have to define another variable z, which is x2. Now, in place of x2, I could have put z as anything else, then also you will get the same answer. So, clearly Sx is 0 1 0 1, Sx naught is 0 1 cross 0 1, I define another variable z is equal to x2. Then the transformation h yz, which is h of x1 x2, x1 plus x2 x2 to R2 is 1 1 on Sx naught. What are its inverse transformations? So, your x1 plus x2 is y, x2 is z. So, x1 is, that means y minus z, and x2 is z. So, my inverse transformation is h1 inverse yz, x1 which is y minus z, h2 inverse yz which is x2 which is z. So, 1 1 transformation is this thing. My whole transformation is 1 1 on whole of Sx naught. So, I just consider the Jacobian transformation. So, Jacobian would be del h1 inverse by del y, which is 1, del h1 inverse by del z minus 1, del h2 inverse by del y 0, del h2 inverse by del z, which is 1. So, Jacobian turns out to be 1 minus 1 0 1, which is 1. Let us look at where does Sx naught goes to 0 1 cross 0 1 through the transformation x1 plus x2 and x2. So, that is what my y and z are. So, that means my x1 is nothing but y minus z, x2 is same as z. I know that my x1 and x2 both are between 0 to 1. So, that means y minus z is between 0 to 1 and z is between 0 to 1, because x1 was between 0 to 1 and x2 was between 0 to 1. So, h of x naught turns out to be collection of all those yz belonging to R2 such that y minus z belongs to Sx naught. Now, y minus z belongs to Sx naught if and only if y minus z is between 0 to 1 and z is between 0 to 1, which is equivalent to saying that y is between z to z plus 1 and z is between 0 to 1. So, Hx naught turns out to be collection of all those yz belonging to R2 such that y is between z to z plus 1 and z is between 0 to 1. Now, here you can see the support Hx naught, here range is depending on each other. So, we cannot say that x1 plus x2 and x2 would be independent. So, but before that let us try to find out the joint PDF of yz, yz. So, which is same as joint PDF of x1, x2. I put the inverse transformation, which is y minus z, z. I Jacobian is 1. So, Jacobian is 1. I hsx yz. fx1 x2 y minus z, z would be nothing but 4 times x1 x2, 4 times z y minus z, as long as z is between 0 to 1 and y minus z is between 0 to 1, which is what is happening over here. So, that is why this quantity. This will be 0 otherwise. Now, I have to find the PDF of y. Now, clearly since z is between 0 to 1 and y is between z to z plus 1. So, that means y can be anything from 0 to 2. So, support of y would be 0 to 2. So, for y belonging to 0 to 2, I try to see the marginal of y. So, I have to integrate z. Note that z is greater than 0 as well as, so what is the range for z for fixed y? So, z is greater than 0, less than 1, z is greater than y minus 1, less than y. So, if we combine this becomes z is greater than or equal to maximum of 0, y minus 1, less than minimum of 1 and 1. So, this is what you get. For this range to be meaningful, minimum of this would be greater than or equal to maximum. So, each of that means 1 should be greater than 0, 1 should be greater than y minus 1, 1 is greater than or equal to y minus 1, that means y should be less than or equal to 2, which is happening. So, this is a meaningful range. Now, if you simplify, so you have to break it into two parts, y is less than 1 or y greater than 1. So, between 0 to 1 this will be this integral, between 1 to 2 this will be this integral. So, you get the marginal PMF of y. Now, let us consider the third method, which is the movement generating function technique. Now, in this case, suppose m is the MGF of some known distribution d1. So, suppose I know that m is a MGF of a known distribution d1. Now, if we can show that my given random variable x has MGF m in a neighborhood of 0. So, that means in that case I know that m, my random variable x has the movement generating function whose distribution is same as d1. But I know that movement generating function determines the distribution uniquely. So, in that case we can say that x has distribution d1. So, one can use the movement generating function also to find the distribution. So, to see this example, let us consider an application of this, consider this example. So, let x be a random variable with MGF given by this, and then suppose you have to find the distribution of y is equal to x square. Now, we know that mt is expected value of e to the power tx, which is same as summation x belonging to Sx e to the power tx fx. Note that it is coming as e to the power t multiplied by certain factors. Certain factors are 1 by 4, 1 by 2, 1 by 4, which turns out to be sum to 1. So, from here I can immediately guess that this is MGF of a random variable x having PMF probability x equal to x, which is 1 by 2 if x is 0 and 1 by 4 if x is between minus 1 to 1. That is what is happening over t. When x is 0, e to the power t 0 will contribute 1, so 1 by 2. When x is minus 1 and 1, it has probability 1 by 4, so it will e to the power minus t by 4 will come as a contribution, and e to the power t by 4 will come as a contribution. So, that is what is happening over here. Now, suppose I have to find the distribution of y is equal to x square. Now, support of x is 0, minus 1 and 1. So, support of y would be 0 or 1, and the probability mass function of y would be fyy, which is probability x square is equal to y. Now, if y is equal to 0, then I have to find what is the probability x square is equal to 0. Probability x square is equal to 0 means probability x equal to 0, which is same as half. Then probability x is equal to y for y is equal to 1 is probability x square is equal to 1, which is same as probability x is either minus 1 or 1, which is same as probability x equal to minus 1 or probability x equal to 1. Each of them is 1 by 4, so sum of the probability would be half. So, this would be half if y is equal to 1, and this would be 0 otherwise. So, you saw that sometimes if you can identify the movement generating function, then this technique can also be useful to find the distribution. Now, before I end this module, let me give the following take home problems. So, let x1, x2, x3 be IID random variables with common PDF given by this. Let t is same as x1 square plus x2 square plus x3 square. Find the distribution function of y and hence find the PDF of y. In the second part, find the PDF of y directly using. So, what one can do is one can use the Jacobian method over here, and one can use spherical coordinates transformation x1 is equal to r sin theta 1 sin theta 2, x2 is r sin theta 1 cos theta 2, x3 is r cos theta 1, where r is greater than or equal to 0, theta 1 is between 0 to pi, theta 2 is between 0 to pi. So, one can use these transformations. So, the second take home problem is as follows. So, let x1, x2, xk be independent random variables with xi having a probability mass function given by this, and I choose x p to the power x 1 minus p to the power ni minus x if x is from 0 1 to ni, 0 otherwise, Now, here ni's are positive integers, p is between 0 to 1. So, they are parameters of the distribution. So, that the random variable y is equal to summation I is equal to 1 to p x I has this probability mass function. So, what I would suggest is use the MGF technique to prove this. So, you will have to find the MGF of this. Once you have MGF of this, you know the MGF of this, and try to show that MGF of y is same as the MGF of this. So, this was all for this module. Thanks for your patience, and have a great day.